Okay, so next we take up the exercises on isomorphism of groups, and this is the first one, the 31st one of this chapter. So we are given 3 pairs of groups, and in each pair we have to explain why the 2 groups are not isomorphic to each other. So the first pair is these 2 products. In the first one we have 2 groups, 2 copies of Z4, and in the second one we have 3 such groups. One of them is Z4 and then 2 copies of Z2. Now we know from properties of isomorphic groups that if 2 groups are isomorphic, then they should have the same number of elements of a given order. For example, if these 2 groups are they are not, okay, had they been isomorphic, both of them should have had the same number of elements of order 2, say. Okay, but that's where they are not the same. That is, we are now going to show that the number of elements of order 2 in this group is different from the number of elements of order 2 in the other group. So let's start the solution accordingly. The elements of order 2 in the first group are these. Okay, so the first group has 3 elements of order 2, and if you are wondering how we know this, you can just simply write the elements and see what their orders are. Okay, it's not a very big task. Whereas the elements of order 2 in the second group are these elements. Let me just write what they are: 0, 0, 1, then 0, 1, 0, 0, 1, 1, yes. Then 2, 0, 0, 2, 1, 0 and 2, 1, 1. So the first group has only 3 elements of order 2, whereas the second one has 6 elements of order 2. So they cannot be isomorphic. Hence, this is not isomorphic to this group. Now you watch something about this solution. In fact, there is no need to find all the elements of order 2 in the second group, since lack of isomorphism will be established if you can show that the numbers of elements of order 2 are not equal. So for example, here you find how many elements of a given order there are in a given group, say this one. Okay, here we have completely found all the elements, so we know that precisely there are 3 elements of order 2 in the first group. Then in the second group, in search of elements of order 2, if you have found 4 already, then you know that the numbers cannot be equal, so you can stop here itself. Okay, however, I have just simply decided to show all the elements, but there is no need. If you have already found 4, then There may be others, for example here 2 more are there, there may not be, but that does not matter since it cannot be less than 4. Once you have reached 4 elements of order 2, it can only be that either 4 or more than that. So the numbers anyway are not equal, so the groups cannot be isomorphic. Number 2, we also know that if 2 groups are isomorphic, then they are either both abelian or both non-abelian. Here, however, in the second pair of groups, the first group is the general linear group. What are its elements? Its elements are non-singular 2 by 2 matrices with real entries. And we know that this group is non-abelian. But the second one is abelian, so they cannot possibly be isomorphic. Since the general linear group is non-abelian, but the group of real numbers, of course under addition, under multiplication, the entire set of real numbers cannot form a group. So if simply R is given, we know that the binary operation is addition, is abelian but is not abelian, but this is abelian. So the general linear group is not isomorphic to the group of real numbers. Lack of isomorphism is somewhat easier to prove than to prove that 2 groups are isomorphic, because to show that 2 groups are isomorphic, you have to show that there is an isomorphism. But lack of isomorphism has many ways of showing it. Say the groups should share some property, but they are not sharing that property, so that means there is no isomorphism. This is not isomorphic to R. Well, let me just tell you something about this word abelian. In Herstein's Topics in Algebra, Herstein is writing abelian with a small letter a, but in Gallien's algebra, contemporary algebra, capital A is written. In this book, in Lee's book, I forgot what the thing the author is doing about this. So I am just simply writing capital A. It may be small a, okay. If it is so, then change it accordingly. I really don't know whether we should write capital or we should write small, or what the rules are. But the mathematics is what matters, okay. And then 3. In case of 3, these two are not abelian because the first one is cyclic. This is something we know, but the second one is not cyclic. Why this is not cyclic, that is given there in the answers that you find at the end of the book. Okay, some selected odd numbered exercises have answers. So this one also has a hint at least. Okay, so you go to that part and you see what is written there. I am just simply going to mention that this is cyclic but this is not, so they are not isomorphic. Since this is cyclic but z times z is not, they are not isomorphic. Okay, so that is the solution. Next exercise 2. Exercise 2 is also similar. Here also 3 pairs of groups will be given, but instead of showing why they are not isomorphic, it's a little open-ended. Open-ended in the sense that we have to first of all figure out whether the two groups are isomorphic or not, and then justify. So it's not given that they are not isomorphic, they may be isomorphic as well. So the second one is 32. Again, for each of the following pairs of groups, explain why they are or not isomorphic. Okay, so what are the groups? This and this, product of 3 copies of Z3. Number 2, Z20, Z21 you may call it Z21, okay, if you are from the US. So it's Z for you. Z21 and Z3 times Z7. Then, oh, here we do not have just 3 pairs but 4 pairs in fact. U22 and Z10. Okay, and the fourth one is this D20 and Z2 times Z10. Okay, so let's see. Number 1, these two are not going to be isomorphic again because they have different numbers of elements of order 3. So let us first see what the elements of order 3 are in the first group. The elements of order 3 in the first group are these elements. Well, the first factor is Z9, so there will be quite a few options. Anyway, so these are the elements. Three, 1, 3, 2, then 3 more, 6, 0, 6, 1 and 6, 2. And whatever I said about such a situation in the previous exercise, here we are going to do that. That is, we are not going to find or write all the elements of order 3 in the second group, but we will just stop our search for such elements in the second group when we exceed the number that we see here. How many are here? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so if we exceed 8 elements in the second group, all of which have order 3, then we stop, because then the numbers cannot possibly be the same. So let us write like this: the group this has more elements of order 3 than 8. To make it somewhat more clear, let us also add here so how many we have found here? 8, no? 1, 2, 3, 4, 5, 6, 7, 8. So let's write like this: 9 of which are as follows. Zero, 0, 1, 0, 0, 2, 0, 1, 0, then 0, 1, 1, then 0, 1, 2, 0 to 0, 0 to 1, 1, 2, 3, 4, 5, 6, 7. We have written only 7. Then 0 to 2. So we have hit that number 8, but one more. Let's say 1, 0, 0. Okay, so this is not isomorphic to the product of 3 copies of Z3. Alright, then what about the second one? For the second one, actually they will be isomorphic, and that fact is a consequence of the fact that these 3 and 7 are relatively prime. But how? How can you set up an isomorphism between this group and this group? For that, you have to go back to example 416 of this section. There, a similar situation occurs when the author considers these two groups, Z15 and Z3 times Z5. It may be in the other order, okay, Z5 times Z3. I don't remember exactly, but these are the components involved in that, and these are the groups that you have in that example. And in that example, if you study the example, you will understand what function you have to consider that will give you an isomorphism between the two groups. So the similar thing you have to do here. Everything is exactly similar. Here also you see 3 and 5 are relatively prime, and 15 is the product of 3 and 5. There also 3 and 7 are relatively prime, and their product is 21. Okay, so they will be isomorphic, and let me write the part like this. The groups are isomorphic. Mimic example 416 in order to write a proof of that fact. Then the third one. Okay, so what about the third one? Yeah, these two groups are also isomorphic, and this fact comes from a theorem that you find in this section itself, U22 and Z10. And the theorem is this. You go back to the section, and there you see that if G is a finite group whose order is of this form 2 times P, where P is an odd prime, okay, then G is either isomorphic to Z2P or the dihedral group D2P. And you can see that for both the groups that we have, for both the groups means let's just concentrate on this one. Its order is 10. Let us first see how its order is 10. We know that the order of this group is the Euler function phi value of 22, and there is a way of calculating this. What you do is that the number whose phi value you want, you factorize that number. Let me just show all these details on this side. So what I am saying is that you calculate phi of 22. So the prime factorization is 2 times 11. So by a formula that we know, or which may be available in this text itself, this is nothing but the number itself multiplied by these differences, in which the primes appearing in the factorization appear like this: 2 times 11 times 1 over 2 times 10 over 11. So you can see that after cancellation you are left with 10. So this group also has order 10, and that one of course has order 10. So the G that you have here, in place of G you now have U22. So its order is 10, and 10 is of that form, 2 times 5, where 5 is an odd prime, and that is why U22 is either isomorphic to this, or U22 is isomorphic to this dihedral group. However, we know that isomorphic groups are either both abelian or both non-abelian, and we already know that this group is abelian, but D10 is not abelian, so this cannot be the case. That's why this has to be isomorphic to this, and that's why they are isomorphic. So let's now write the things systematically. We have to refer to that theorem number or whatever it is. Oh, do I have it here? Yeah, theorem 450. So number 3, since, let's write like this: since ideally we should show all these things in the solution itself, but since I am not writing full solutions but rather giving elaborate hints in place of solutions, so I choose to not write these things. Okay, since this is this where 5 is an odd prime, it follows from theorem 415 that U22 is isomorphic to Z10 or D10. Since U22 is abelian but D10 is not, we must have U22 isomorphic to Z10, and that's why the two given groups are isomorphic. I need a little ink, otherwise by the end of the video it will be almost gone. And now we have the fourth part. In the fourth part, the groups are what? D20 and Z2 times Z10. And this is rather easy. We already know that D20 is non-abelian, but Z2 times Z10 of course is abelian because both the factors, that is Z2 and Z10, are abelian. So that's why they cannot be isomorphic. Since D20 is non-abelian but this is abelian, the groups are not isomorphic. So that is the solution. And let us see one more. Let G be the, okay, let G be the set of all matrices of the form this. Lower triangular matrices, that is matrices in which the upper off diagonal part, the upper triangular part has all its entries 0. In this case that is just one entry, the first row second column entry, but the other entries can be, may or may not be 0. The diagonals are 1 and this entry is anything. Anything means any real number. Is it real number though? Let me just see. No, okay, it's given to be integer. Okay. For all, I mean it is real number, but more specifically it's an integer. For all integers A, show that G is a subgroup of the general linear group of 2 by 2 matrices with real entries. So this is one half of the exercise, and the second half asks to what familiar group is it isomorphic? This group. It is isomorphic to some group that we know, that we already are familiar with. What is that group? Now, although you see two parts in this exercise, but we are going to get the job done with just one step. Means there actually won't be two parts in the solution, but only one part because of a result. So let me just start off with by defining a function. Consider the function, say f, from the set of integers into the general linear group, where the definition of f is like this: f of n is some integer, is equal to this matrix. Alright, there is no problem with this function. So if you take any arbitrary input n from here, so any integer, then the output is this matrix, which for given n is a unique matrix. But is this matrix here? The only condition for a matrix to, 2 by 2 matrix of course, to be in this set, in this group, is that it be non-singular. That is, it should have non-zero determinant. The determinant of this matrix can easily be seen to be 1, so which is not equal to 0. So that's why f is well defined. Clearly, f is well defined. Alright, so now the next thing we do is we are going to show that f is a homomorphism, a group homomorphism for any two integers not necessarily distinct. We have note carefully that the binary operation in the first group is addition of integers, but in the second group the operation is multiplication of matrices. They are two entirely different things. Okay, so what we do, so because the operation here is addition, so we add n and m up and apply f on that. So this, by the definition of f, will be this matrix. Now the question is this matrix equal to this product? Let's actually calculate. 1 times 1 is 1, plus 0 times m is 0, so that means 1. Okay, 0 plus 0, 0. n plus n, n plus n. 0 plus 1, 1. Yes. So that's why this is f of n, of course, times this is f of n. So f preserves binary operations between these two groups. Thus, f is a homomorphism, a group homomorphism. Now next, let us show that this homomorphism is actually one-to-one. Okay, that is equivalent to showing that the kernel of this homomorphism consists only of the integer 0. That is, it's the trivial subgroup of this. So let n be any element, let's call it something else. Say k be any element in the kernel of f. Then okay, so then by the definition of kernel, f of k will be what? F of k has to be the identity element in this group, which is what? The 2 by 2 identity matrix. It's not the zero matrix, okay? The operation is multiplication of matrices, not addition of matrices. Then f of k is this. But we know what f of k is from the definition of f. We have this. So this implies k has to be equal to 0, i.e. the kernel of f is the trivial subgroup consisting of only the identity subgroup of this, of course. So that means f is one-to-one, f is injective. F is one-to-one. Now you recall a result, theorem 412, from the section on homomorphisms. What it says is this: suppose G1 and G2 are two, it says many things, okay. One among those parts is that if you have a homomorphism, something, say F, between two groups G1 and G2, and suppose that H is a subgroup of G1, then f of H must be a subgroup of G2. This is a consequence of having a homomorphism like that. In our case, what we have is this. Now, for the subgroup H, we can consider Z itself because it's a subgroup of itself. So, f of Z should be a subgroup of the general linear group, but the way we have defined the function f, clearly f of Z is nothing but that set of such matrices that is mentioned in the exercise. Now, by so what is that result? Theorem 412. F of Z, let's just write it in the as a set what it is a subgroup of the general linear group. We could have written this conclusion after showing that f is a homomorphism, because all we need for this is the function to be a homomorphism. That's it. The function being one-to-one as well is extra. Okay. However, what do we achieve from this one-to-oneness? We achieve this. Since f from this to the general linear group is one-to-one, the function or map, if you change this general linear group and replace it with the image of z under f, we can do that. We just change this, then this function will be, it will remain one-to-one of course, but now it will be additionally onto, because all we are considering now are the images and not things that lie outside of the image set. Is, so being one-to-one and onto, it becomes a bijection, and at the same time it's a homomorphism, so it's a bijective homomorphism, or in other words an isomorphism. Let's write that is an so that means what? First of all, we showed that the set in question is a subgroup of the general linear group. So that is the first part. And in the second part, now we can say that the set turns out to be this. No, this is isomorphic to a familiar group, and that familiar group is the additive group of integers. So this is isomorphic to the familiar group. Yes. So that's it. So that's how we have managed to prove both the parts in the exercise. And let me just end the video here itself. We will of course continue with what comes next in these exercises in the next Lee update. And tomorrow, as usual, we have our analysis. We have started the chapter on continuous functions, and we have what are the things that we have seen so far? We have seen the notion of adherent points, right? And I think, if I am remembering correctly, we wrote down the basic properties of, we defined closure of sets also, and we then wrote the basic properties of closure, but we did not prove that theorem. So tomorrow we will start by proving that result. Theorem or lemma, whatever it is, we will prove it. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.